Hi everyone, welcome to our 10th lecture. This lecture is on optics and it is for both the calc and the non-calc students. Okay, so what we're going to study today is actually what's called ray optics, and ray optics is actually a subset of the full optics, which would include waves. So if you recall, when we worked on waves, we talked about light, and light turns out to be a wave. Okay, so if you really wanted to study how wave travels through, say, lenses or mirrors or anything like that, to study a property, you would have to treat light as a wave. However, you can, under certain circumstances, treat light purely as a ray and just trace out the rays, and that's the optics that we're going to study, because wave optics is actually very complicated, but ray optics is pretty easy. Okay, so we're just going to study ray optics. So let me start off by describing a wave, which we did study, but it's worth repeating right now, and define what a ray is for a wave. Okay, so if you take a look at this diagram here, suppose you're looking at just waves on, say, a water table. So you're looking down on water. You would see this line here could be like a crest, and then some wavelength away there'd be another crest, and then there's another crest, and then there's another crest, and between the crests there are troughs, which I've drawn in these dashed lines like that, and the crests and troughs would move together to I've drawn here a velocity vector to the right. Okay, and so there you go, there's a set of waves traveling. Okay, and light travels that way. The ray for the wave is actually defined as a line which is perpendicular to the wavefronts and points in the direction of the propagation of the waves. Okay, so you can see here this ray, it's perpendicular to the crest, and it's also perpendicular to the troughs, and it points in the direction of the velocity of the wave. Okay, so for ray optics, you don't have to worry about the crests and troughs, the wave structure of the wave. All you have to do is just follow these rays and see where they go as they propagate. We actually did do this already when we talked about refraction and reflection, and in fact, that's all we really have to look at when we do ray optics here, is reflection and refraction. Okay, the other two phenomena, which were diffraction and interference, they were very much wave phenomena. Okay, you had to talk about crests and troughs. Okay, so we don't have to talk about them here because we're just going to reduce it to ray optics. Now, under what conditions are you okay to just do ray optics, to just trace out the rays and not have to worry about the wave nature of light? And that's whenever your optical devices are actually much larger than the wavelength. Okay, so if you remember, like with diffraction, if the hole through which the diffraction occurred was very much bigger than the wavelength, really the diffraction was a very small phenomenon compared to the entire wave. Okay, so whenever your optical devices, like say a lens, like lenses of your glasses, okay, whenever they're much bigger than the wavelength, so then you don't have to worry about the wavelength, and you can reduce down to ray optics. Okay, so how big is the wavelength of light? And light has a spectrum. It goes all the way from like violet to red, and at the violet end, which is the short wavelength, then the wavelength is 380 nanometers. So remember, nano is 10 to the minus 9, or billionth. Okay, so this is billionths, 380 billionths of a meter. Okay, and at the other end, the red end, which is the long wavelength, then it's 740 nanometers. Okay, so that's the spectrum of visible light, and that's really small. Okay, it's definitely much smaller than say 3 or 4 centimeters, which is the width of the lenses of your glasses or whatever. And so we really don't have to worry about diffraction and interference effects. All we really have to worry about is tracing the rays, and that's what ray optics is all about. Okay, and like I said, we already did that with reflection, and we already did that with refraction. Okay, so now you could say to yourself, well, how would I make an optical device something which guides the rays of light? How would I do that? Well, for reflection, it's easy. You'd use a mirror. Okay, so mirrors are optical devices which are based on reflection. All right, and lenses. What are lenses? Well, they're like glass or plastic or something like that, and there the light is traveling from air into the glass medium and then back out into air. And you remember, when light travels from one medium to another, it will refract, and so lenses are based on refraction. Okay, and both reflection and refraction can be totally studied using ray optics. All right, so let's start off with mirrors. Now we're mostly going to concentrate on lenses, so I want to get the mirrors out of the way. But there's a relationship between how mirrors work and how lenses work, okay? And we'll see that as we go along, okay? Now there are three different types of mirrors that you can make. The most obvious one is the most boring, and that is just a flat mirror. This is like the mirror in your bathroom, you know, that you look in the morning, okay? A flat mirror like that doesn't have very interesting optical devices, optical properties, okay? And so we're really not going to study those, okay? But you can have concave mirrors and convex mirrors. So concave are mirrors which are hollowed out in the middle here like this, okay? And the shiny side is on this side like that, all right? And so you can see that it's kind of like a cave, so it's called concave, all right? Convex are the other way around, all right? It's a little harder for me to do with my hand, but you can imagine that the shiny side is out here, okay? And those are called convex mirrors, okay? And so let's start off by looking at how the rays are traced for a concave mirror, okay? Now, like I said, we're not really going to study this one in detail because we're going to study the lenses in detail, but it's going to turn out that concave mirrors are actually related to convex lenses and vice versa. So by studying the lenses, we've effectively studied the mirrors as well, okay? So here is a schematic diagram of a concave mirror. All right, how does this concave mirror work? Okay, so you see the hash lines there. That's the side that's you know, the opposite side of the mirror, the non-shiny side of the mirror, and the inside here is the shiny side of the mirror. Okay. Now, the way I've constructed this mirror is that it's part of a circle, so it's a semicircular mirror. Okay, and you can see this point C here. That's the center of the circle. Okay, so the radius would be from this point C here right out to the mirror there like that. Okay, and I didn't draw the whole mirror because that would clutter the diagram. I just drew the whole circle. I just drew a portion of the circle like that. Okay, but if you were to draw the whole circle, it would go all the way around here like this, and it would be a circle centered on that point C. Okay, now how do the rays travel when they impinge on this mirror? So you remember from our study of waves with reflection, if you follow the rays of the waves, the incident angle is equal to the reflected angle for reflection. Okay, it's very simple. So whatever angle the ray makes to the normal on the way in, it makes the same angle to the normal on the way out. Okay, so what I have drawn here is I have this semicircular mirror here like that, and I drew the axis here like that, and the axis is just a line through the middle of the mirror passing through the radial point there, the center C, okay, like that. Now, if you take any ray of light that's traveling parallel to that axis, like say this ray right here, you see how it's like a ray, and I even drew little arrowheads there to show you that it's coming in. So if you drew that ray in like that, it comes in and it impinges on the shiny side of the mirror there like that, okay, and it reflects such that the incident angle is equal to the reflected angle. Now I didn't draw the normal here because that would make it really hard to see this diagram, but if I drew that normal in there, you would see that the angle that it makes to the normal on the way in would equal the angle that it makes to the normal on the way out. So the ray gets reflected at that shiny surface and it passes out, and it doesn't pass out through that point C, it actually passes out through another point which we'll call F for focal point, okay? And so this ray comes out here like that, and it passes through this point F, which is on the axis, like that, right there, and then it goes along like that in a straight line, all right? So, you know, you pick any ray that comes in parallel to the axis, it impinges on the ray, and it reflects and it goes out through that focal point. And it could be any ray. I just did one here, I showed another one here. So here's another ray coming in, and it's closer to the axis than the first one, okay, so it comes in like that, and again, incident angle is equal to the reflected angle, and it reflects out, and it turns out that if you do the geometry properly, which I'm not going to do for you, but if you do that geometry properly, all of those rays will pass through this focal point and then go out straight like that, okay? So the question is now, where is that focal point, all right? And it turns out that if you do the geometry correctly and you draw it out such that the incident angle is equal to the reflected angle, it turns out that the focal point is half of the radius of the mirror. Okay, so the radius of the mirror, even though I drew the point C there, I called it C because that's the center. Okay, the radius would be from C to the mirror like that. Okay, it's like the center of a circle. Okay, C is at the center of a circle. So of course, if you measure from the center to the mirror itself, that would be a distance r, the radius. F is halfway between C, and the mirror. Okay, in other words, F is half of the radius of the mirror, like that. Okay, so there you go. This is how a concave mirror works. All right, haven't talked about how images are formed or anything like that, but there you go. All right, and we call it semicircular because, of course, you can't make it a full circle, because then how would you get the rays in there? But if you take a mirror, like a circle, and you just cut off a piece of the circle, and that forms your concave mirror, it will act like this, such that all rays that come in parallel to the axis will bounce off the mirror and then pass through that focal point. You might ask the question, what happens to rays that don't come in parallel to the axis? Well, hang on. That's when we get to the lens. We'll talk about that. Okay, but there we go. There's the concave mirror. All right. Now the next one that we might look at is the convex mirror. So the convex mirror, like I said, is the opposite of the concave mirror in the sense that it's also, we'll make it a semicircle. Okay, so that means it's circular, centered on a point C, like that. All right, but now the shiny side is this outer side here, like that. Okay, and the dark side is on the inside, like that. The non-shiny side is on the inside. Okay, so the shiny side on the outside. And once again, you know, it's a semicircle, and it's centered on some point C there, like that. Okay, that's the center of the circle. So the distance from C to the mirror itself, or from C to any point on the mirror, would be a distance r, the radius. All right, now what happens this time when you send in rays that are parallel to the axis? Okay, so these rays that come in parallel to the axis, they will once again bounce off of the surface. They'll bounce off such that the angle made from the ray to the normal, the incident angle, will equal the ray that goes out, the angle of the ray that goes out to the normal. Okay, in other words, the incident angle will equal the reflected angle again. And so you can see here we have a ray, and it'll bounce out like that. Okay, and then we have I put another ray here like that, and this one's closer to the axis, and it'll also bounce out. Now, because these are bouncing out, they're not passing through a point anymore on the axis. But if you extended them backwards, like the reflected ray here, see this part here is this reflected ray here. If I were to extend it backwards, that's what this dashed line is. It looks like all of the rays are emanating from this focal point on the other side of the mirror. Okay, so once again, here's a ray coming in, it bounces and it goes out like that. Okay, this ray, the outgoing ray, looks like it's coming from the focal point. All right, it actually isn't, but it looks like it's coming from it. That's what that dashed line is. It's extending it back. So here's another ray that comes in, impinges on the convex mirror, comes out like that. And if you were to extend that ray back along that dashed line, it also looks like it's coming from that focal point. And if you ask the question, how far is that focal point from the mirror? Just like with the concave mirror, with the convex mirror, F is half of the radius of the semicircle. Okay, so that's how a convex mirror works. All right, and once again, you still have that. Now, that's all I'm going to say about mirrors. Okay, we're really going to study lenses because lenses are more interesting and they're also more common. Okay, unless you're making something like a reflecting telescope or something like that, you're probably not going to be working with mirrors. You'll probably be working with lenses. All right, so you know, like how do our eyeglasses work? Right? And so let's look at lenses. Now, what I just said about the mirrors actually translates over to lenses quite smoothly. It just turns out that the concave mirrors behave like convex lenses, and convex lenses work like concave mirrors. Okay, so if you understand how a convex lens works, then you can work with concave mirrors. And conversely, if you understand how concave lenses work, then you understand how convex mirrors work. Okay, there's only one tiny difference between the two, and that is that lenses work because of refraction, while mirrors work because of reflection. Okay, and refraction, you remember, is governed by Snell's law, and there it is. Okay, and I didn't tell you everything about Snell's law. There's the index of refraction, like N1 and N2, and remember, those are the index of refractions of the two different media. Okay, in the case of, say, eyeglasses, that would be the glass of the lens, that could be like N2, and air would be like N1. But these index of refractions actually have a little bit of a dependence on the wavelength of the light. In other words, the index of refraction for a red light is a little bit different than the index of refraction for violet light. Okay, and then the whole spectrum, okay, the whole rainbow. Okay, and what that means is that when you actually undergo refraction, one frequency of light will refract more than another. Okay. Now, before I showed you that for a prism, because that's how prisms separate the colors of light into a rainbow, let me just show you how a prism works. Okay, so we understand it. So over here, we have air out here, and then this triangular piece here. I didn't close the triangle, but this whole area here where my cursor is, that whole area is glass. Okay, and then of course there's air on the other side. Now, if a ray of light comes in and it impinges on the interface between air and glass, remember what happens? Because glass has the higher index of refraction, the ray will bend towards the normal. And again, I didn't draw the normal. It would kind of be like that, it would be perpendicular to the surface, to the interface. Okay, but you can see that ray here inside the glass, the refracted ray, it's a little bit closer to the normal. Okay, and then of course, the ray would travel through the glass, but eventually it would get to the other side. And that's the other interface between glass and air. And it would then bend away from the normal on the other side. And you would get this kind of like path like that. Okay. And there'd be some angle there, which I called phi. And that angle phi is how much the ray got bent by the prism. Okay, so it comes in, the ray comes in, bends towards the normal, bends away from the normal like that, and you get this deviation from the original path, phi. So if you were to follow if the prism weren't there, the ray would have followed along this dashed line here like that. But because of the presence of the prism, it bends and bends, and it bent through that angle phi in there like that. Okay, and here's my claim: the angle phi can be calculated using Snell's law. All right, I'm not going to do it, but I think you could imagine how you would do that. You'd have to apply Snell's law twice, and you'd have to do a whole bunch of geometry because the triangular shape of the prism. But you could calculate how much phi would be. But here's my point: phi is going to depend on the frequency of the light, or the wavelength of the light, so that one color light won't bend as much as another color of light. All right, and then we get this situation here. Okay, so we'll have like white light coming in, and because the red turns out to not bend as much as the violet, because the index of refraction is wavelength dependent, the red will follow this path up here like that and there, and we will get red up at the top. Okay, but because the violet bends more, the white light, which is made up of the entire spectrum, the entire rainbow, the violet will bend more, and it will turn out to be at the other end of the rainbow. Okay, so I'm going to talk about what white light is in a minute, but right now you can imagine white light is being made up of all the possible wavelengths, and when the wavelengths they get to the prism, red light will bend less and the violet light will bend the most. So red will bend the least and the violet will bend the most, and then all the other colors in between will bend proportionally, and what you get is a rainbow. And that's exactly why you get a prism will break up white light into a rainbow. And you know this probably from high school. The colors of the rainbow are red, as that's a long wavelength, okay, and then orange, and then yellow, green, blue, indigo, and then finally violet. Okay, and so there you go, there's the entire spectrum. And the reason it's broken up is because red has the longest wavelength, orange a little bit shorter, yellow a little bit shorter, green shorter yet, and then finally we get down to the violet, which is the shortest wavelength, and that's the one that gets bent the most. Okay, now I introduced this because I said lenses work on refraction and mirrors work on reflection. This doesn't happen with reflection. All of the wavelengths will bend the same because the incident angle is equal to the reflected angle for all the different wavelengths. But here, the refraction is different for all of them. Okay, so there's a difference between the two. Okay, now for what we're going to study is we're not actually going to worry about the different frequencies. Okay, so we're just going to assume that the ray doesn't get broken up. All right, now that is an assumption, but in reality it does, and that means that if you don't design your lenses right to take this phenomenon into account, then what your lenses will do is you'll look at something and like say you have eyeglasses and they don't take this effect into account, then everything will have like a rainbow haze around it. Okay, and the reason that rainbow haze would exist is because again the lenses are working on the basis of refraction, and they're refracting the red light differently than the violet light, and so you're going to get a rainbow haze around everything. Okay, so we're just not going to worry about that because that would complicate things. But it is an important difference between the two. Okay, so I said I was going to say a little bit more about white light. Okay, or light in general. All right, so if you have light of one particular color and one frequency, well then like it'll just operate as a single ray and so on, and you wouldn't know anything about what about the phenomena that I just told you about. Okay, but if you take what you consider like white light or some composite light, and you pass it through a prism, you're going to find some surprising things. Okay, because it'll break it up into the rainbow, but what you think is white light may not really be exactly like a uniform spectrum of light. So let me describe what I mean by that. If you take a light from the sun and you pass it through a prism, you're going to get the entire rainbow, and it'll be uniform across. Okay, so well, maybe the yellow light will be a little bit brighter, but it'll be uniform colors all the way across. And the reason that happens is because light from the sun is basically light from a hot object. Okay, now this is what in physics is called black body radiation, and the name is a little bit of a misnomer. The reason it's called black is because black is an absorber of light. So we're not talking about an object which is produces light itself. It's actually an object which will absorb light. But when you heat an object up enough, it'll start to glow, and it'll glow because of the heat in that object. Okay, so if you take a poker and you put it in a fire, the poker will start to glow red, okay, a dim red, and then as it gets hotter, it'll glow a brighter red. If you make it hot enough, it'll eventually start to glow white, okay, and what's that spectrum of light? It turns out that with black body radiation, you get the full spectrum of light. Okay, now that's different than, say, the white light that you might get from a fluorescent light bulb. All right. By the way, the black body radiation is the kind of light that you would get from an incandescent light bulb. So incandescent is the ones with the filaments, and the filaments get hot and they glow. Okay, and that hot glowing filament is what produces the light. Okay, just like the sun produces it through this black body radiation. But there is also these fluorescent lights. Okay, and you might wonder, geez, how do fluorescent lights work? And fluorescent lights, what they do is they have a gas in there, and the gas gets electrified, and then the gas glows. Okay, and it turns out that light it looks kind of white, but you've often seen that the fluorescence light have a kind of a funny color to them. Okay, they're white, but they're not quite right. All right, and what's going on there is you don't have the full spectrum. You actually have discrete lines of colors. And you might wonder what's going on there. So this is the opposite of black body radiation. This is light that is produced from atoms when the electrons jump between orbitals. Okay, so you may know this from your chemistry, but atoms are made up of the nucleus, which is positive, okay, and these electrons which orbit the nucleus. All right, now they orbit the nucleus, but they do it in a very funny way. They don't just have any old you can't just have any old orbit. You only have discrete sized orbits. So you have a smaller orbit, okay, n equals 1, and you can have another orbit which is n equals 2, and then n equals 3, and so on. You're not going to have n equals 1.5 orbit. Okay, so you can have like an n equals 1 orbit and an n equals 2 orbit, but you're never going to have an orbit which is just like halfway in between. And you might wonder, why does that happen? Why are these electrons are orbiting, but they're orbiting in these discrete orbits? Okay, so n equals 1, n equals 2, and so on. You go, well, why can't they orbit in any old radius? Okay, and the answer ultimately is quantum mechanics, but you can think of it this way. The electrons in the atom, they're really not particles. Okay, they're acting more like waves. And you remember the standing waves that we studied? Those standing waves, remember how like you could only have certain shaped standing waves because you tied them down at two ends, and so you could have like n equals 1, or you could have n equals 2 with like two antinodes in there, okay, like 2 bubbles and then 3 bubbles. So you could have n equals 1, n equals 2, n equals 3. The motion of electrons around an atom are actually more like standing waves than they are like planets orbiting the sun. They can't just orbit at any old radius. They actually, because they're tied to the nucleus, by the electrical force, they actually act like standing waves. Now, I know that might sound strange because you say, well, isn't an electron just a particle? Yeah, I know, but this is the mysterious world of quantum mechanics. And so, for at least for as far as this phenomenon goes, it's easier to understand these electrons as kind of like standing waves. And so they can either be orbiting at n equals 1, or they could be orbiting at n equals 2, and they could be orbiting at n equals 3, but nothing in between. Now, what happens is these electrons, they can jump between the orbits. So if you give them some energy, so say they're in n equals 1, you give it some energy, that electron can pop into n equals 2. Okay, now how it gets in between there, let's not worry about that. But it's like it starts at n equals 1, give it some energy, it's in n equals 2. Give it more energy, it goes to n equals 3, and so on. Conversely, it could be in n equals 2, and it could give up some energy and then go down to n equals 1. Okay, it can't give up energy n equals 2, and it can't give up energy and then go down to n equals a half or 1.5, or it can't be in like n equals 1 and then you give it some energy and it pops up to n is equal to 1.5. It's always got to jump between discrete integers, so like 1 to 2 and so on. All right, now those discrete energy jumps turn out to be discrete colors. All right, and so when the atoms inside the fluorescent light bulb are actually giving off their energy, their electrons are jumping between different shells. Okay, that's what they're called in chemistry, different electron shells. And when they jump between these discrete electron shells, they give off light of a particular color. And if you take a prism and you break up the light from a fluorescent light bulb, it actually turns out that you don't see a whole rainbow. You just see these discrete lines, like say a purple line, and then you might see a green line, and you might see a yellow line, and then a red line. And you say, well, where's the blue line, or like an orange line? Well, it's not there. It's just not there because you've just got these discrete colors, and those discrete colors correspond to the discrete jumps between the different shells. Okay, so this is very different than the black body radiation, which is the full spectrum. This is just purely because of transitions of electrons within atoms, between the shells of an atom. So to make this more concrete, this is a hydrogen atom. Okay, if you take a look at the hydrogen atom, which has been studied quite a bit, okay, there are these shells, like there's n equals 1, 2, 3, and so on. The transition from n equals 3 down to n equals 2, so we're at 3 and we go down to 2, we give up some of the energy. That can be measured, and it turns out that light can be measured. And it turns out that light, when the electron goes from shell equals 3, n equals 3 to n equals 2, is 656 nanometers, okay, which puts it into the red spectrum, okay. A transition from n equals 4 to n equals 2, that's a little bit further out, okay. So 3 is here to 2. Well, 4 to 2 is going to be a bigger transition, so it's a little bit more energy, and that's a little bit shorter wavelength. That turns out to be 486 nanometers. From n equals 5 to n equals 2, it turns out to be 434 nanometers, okay? And then from n equals 6 to n equals 2, it turns out to be 410 nanometers. And so what you would see if you actually took hydrogen and you put it like in a fluorescent light, okay, basically just hydrogen inside of a glass tube, and you put an electric current through it, so that the hydrogen starts to glow, okay, you would see what looks kind of like a reddish kind of light. But if you put that light through a kind of pink, actually, if you put that light through a prism, what you would see is you would see a red line, and then you would see these other colored lines here. I don't know exactly what color they are. They look like they're in roughly the blue range there. And then you would see a purple line, okay? And so that's the, you would see four lines, okay? So that's the spectrum for the hydrogen atom, okay? Now notice that they all end up in n equals 2. For the visible range, they have to start at whatever the higher shell is. It could be like 3 or above, okay? But they have to fall down to n equals 2. That turns out to be what's called the Balmer spectrum, and the Balmer spectrum is actually the visible spectrum for hydrogen. But there's others. You could drop down to n equals 1. And so if you go from a higher level down to n equals 1, that's called the Lyman series, but we can't see that. That's in the ultraviolet, beyond our ability to see. And then if you drop from a higher level down to n equals 3, that's called the Paschen series, and that's in the infrared, and we can't see that either, okay? But basically, that's what these fluorescent lights are. Now, the fluorescent lights that we use don't use hydrogen. They use other gases, okay? But still, it's the same principle. It's basically these electrons jumping between the different shells. And in the lab, the optics lab, we actually will take a prism, and we'll actually look at the fluorescent lights, and you will see these discrete lines. Okay, so just to kind of remind you of the two different sources of light. One is just black body radiation, okay, and which I describe here. And black body radiation just means a hot object, okay, an object which is made super hot, okay, hot enough that it starts to glow. And an object which glows will glow, it'll start off if it's not so hot, it'll be a dim red. But then, if you make it hot enough, it'll be white hot. And that's what the sun is. It's just a white hot object. And if you break up that light using a prism, you would see all the colors of the rainbow. The other source of light, and there's still more sources, but the other common source of light would be these transitions of atoms between different shells, okay, transition of electrons and atoms between different shells. And whenever those transitions occur, they're discrete, and so that leads to discrete colors. So you don't get a full rainbow, you just get lines within a rainbow. Okay, now in our eyes, if we have a mix of red and purple and some blue in there, I don't know, it just kind of looks pinkish or something like that. If you have enough of those mixtures, it starts to look white. But that's why our fluorescent lights don't quite look right. They look white, but they don't look like a nice white, and that's because they're we're used to the sun, and these things are just producing they're not producing the full rainbow, they're producing a spectrum. Okay, so a bit of an aside for lenses, but still I wanted to discuss light, okay, because I don't know if any of you will actually go on to work in lens making or whatever, but all of these things have to be considered because the refraction is dependent on the wavelength of light, and so lenses will operate differently on different colors of light, and that has to be taken into consideration. Okay, let's come back to the to tracing the rays for lenses. Okay, so let's start off with a convex lens. Okay, so remember, convex lenses are they act a little bit like the concave mirrors. All right, and we're going to make some assumptions for the ray tracing we're going to do to make life easy for us. Okay, so this is the simplest kind of ray tracing you can do. So what are the assumptions that we're going to make? Okay, so the first assumption that we're going to make is that we'll only look at what are called simple lenses. Okay, and what that means is that the focal point will just be one focal point. All right, and you say, well, what do you mean by just one focal point? Isn't there, I just described the concave and convex mirrors as just having one focal point. Yeah, but because of this business that different colors are refracted at different to a different degree, you could have a lens which has a focal point for red light which is different than the focal point for violet light. Okay, so for a simple lens, we're going to say, you know what, no matter what color light you put through this, all the rays of all the different colors of light are just going to pass through one simple focal point. Okay, and that just eliminates all the concerns about the different frequencies of light. Okay, the other thing is that convex means that the lens has to be thin at the edges and thick in the middle. So it's thick in the middle and thin at the edges. Okay, and that's just purely for geometry. All right, now it doesn't really matter whether both sides of it are curved, or you can have a situation like this where like one side is flat and you just have a curvature there. As long as it's thin on the edges and thicker in the middle, okay, then you're going to get a convex lens. Okay, and the other thing is that the rays passing through the lens, we have to make sure that not only does it have only one focal point, but they'll converge, and they'll converge at a point, depending like how everything is set up, they'll converge at a point where which is not necessarily the focal point. Okay, they'll converge at some point. No matter where that point is, no matter where the point of convergence is, all the rays are going to converge at the same point. So the focal point is where all the points of all the rays coming from infinity will converge. But when we put an object near the mirror, you'll see that they'll get convergence at different points, and those convergence at different points, no matter where that convergence occurs, it'll just be one point of convergence. Okay, you'll see what I mean by that in a minute. Okay, and the last thing I'm going to say about this is that we're going to call it a convex lens, but you probably know this better as a magnifying glass. Okay, so you'll see that when we trace out the rays, that when an object is placed closer to the lens than the focal point, this acts like a magnifying glass. Okay, so yeah, it's a convex lens, but you could just think of it as a magnifying glass. All right, and The magnifying glass, we'll also consider the opposite, which is the concave lens. But the magnifying glass is kind of interesting because there's two cases. There's the case where we can put an object further away than a focal point, put an object further from the lens than the focal point, and you'll get one kind of an image. And you can put the object closer to the lens than a focal point, and you'll get a different kind of object. And we'll consider both of those cases. Okay, so let's start off by first considering the situation where you put an object further from the lens than a focal point. Okay, and so what I have here is a diagram, and it's a schematic diagram. I don't have any rays on it, but I just wanted to define some of the things that we're going to be measuring before I actually start drawing these ray diagrams. Okay, so what you have here in the middle right there is, rather than having to draw that kind of convex lens all the time, a schematic way of drawing a convex lens is to just draw a straight line like this and then put arrowheads at the top like that. Okay, so this middle like double-headed arrow here, like that, up and down like that, that is just a symbol for a convex lens when you do these ray tracings. Okay, so that's what this middle symbol is here, like that. Perpendicular to that is the axis. Okay, and there it is. Okay, so everything is going to be measured with respect to that axis, or either on that axis or from that axis. Okay, so there's this axis in the middle, and it's passing through the middle of our lens like that. Okay, now the lens, being a simple lens, has a focal point, so there's a focal point right here. Okay, and on the other side there's a focal point. So another thing about simple lenses is you could send the rays through one way, or you could send the rays the other way. Because it's a lens, it'll go both ways. The focal length on one side and the focal length on the other side is the same. Okay, so you can see here the distance from that focal point to the lens that I've marked here, F. So that bracket just means the distance from the focal point to the lens. That's the distance F. On the other side, there's also a focal point, and the distance from that focal point to the lens is also F. Okay, so there you go. There's a focal point. All right. Now, we don't want to just do rays that are coming from infinity. All right, we want to do rays that are coming from an object, so we can see what kind of images are formed by that object. So over here, what you do to draw an object is you just draw an arrow. Okay, like that. Sometimes when you see these diagrams in textbooks, they might put a little candle there or something like that. But schematically, it's good enough to put an arrow like that. Okay, and you can see that arrow there. This one's pointing up, and that is called the object. So the object is the source of light. Okay, it's the thing that's going to be sending off the rays, and the rays from the object are going to pass through the mirror, and they're going to be converged by the mirror onto an image. Okay, so there's the image right there. So the image looks like the object. It's also like an arrow. Okay, but it's on the in this case, all right, in this case it's going to be on the other side of the lens. All right, so here's the image and here's the object, and you'll have to label them, because you can see that this is just like an arrow there, and there's an arrow there, and you go, well, which one's the object, which one's the image? You have to indicate that somehow. Okay, so here's the object, and the rays that are going to come off the object, they're going to form an image, and there's the image that's formed. Okay, the object is going to be the source of the rays, and that are going to pass through the lens, and then those rays will form an image. All right, now there's a couple of things about the object. First is, how far is the object from the lens, and that we will call DO. So you can see here that I've drawn this DO, the distance from the object, and bracket there, to the lens itself. That distance DO, that's the distance of the object to the lens. All right. On the other side, you've got the image, and there is a distance between the image and the lens, and we will call that DI for the distance of the image to the lens. Okay, and a couple more things, and then we're ready to move on. The object will have a certain size to it. We can call it the height of the object, because the object, you can put an object anywhere, but for the ray tracing we're going to put the bottom of the object right on the axis, and then the tip of the object is wherever it is. The height of that object we will call HO for height of the object, and of course the image is going to be formed, and it's going to have its own height, and we will call that HI. Okay, so those are all the variables that are going to go into our equations. Okay, let me just go through them very quickly. F is going to be the focal length. It's the distance from the focal point to the lens. Okay, DO is the distance from the object to the lens. DI is the distance from the image to the lens. HO is the size of the object, or the height of the object, and HI is the height of the lens. Okay, These things are going to have a sign associated with them, all right? And so HO will be like positive up, and HI here, you can see it's going down, it's negative, okay? But let's not worry about that. You'll see how the signs work as I work through this, okay? So, all right, and here I just defined that. Right? By far the most important is DO and DI and F, okay? Those are the ones that are related by the lens formula that we'll see in a minute, okay? And, all right, so before we start tracing those rays, okay, you have to say, well, where are those rays? Like, where are they coming from? So the object, any object that you might see, like, I don't know, you look at some object on your table, like your mug on your table or something like that. Every point on that object is emitting rays in every possible direction, okay? So here what I have is like this arrow is supposed to indicate that object, the object, okay? If you take a look at the tip of that object, that tip of the object is radiating rays in every direction, okay? So light is absorbed by the object, and then that object basically reflects it, okay? And it reflects all the rays away from it, okay? So you get like these rays that just radiate out, but every single point, not just the tip, but every single point on that object is going to be radiating rays away from it, okay? We don't have to worry about all those rays because there's rays radiating from the bottom of the object, there's rays radiating away from the middle of the object. We're just going to look at the rays that are radiating away from the tip of the object, okay? And those rays, they're going to radiate out, and some of those rays will impinge on the lens and some of them will not, okay? So let's take a look at this next diagram here. Here you have the object, which I've just labeled with O, okay? So you can see that arrowhead there like that. Again, every single point on that arrowhead on that arrow is radiating rays, but we're only going to look at the rays that are radiating from the tip. Okay, that's the first point. The second point is there are rays that are radiating out every which direction. So there's like a ray that's going to like go off like that, say up at some angle, and it's never going to come anywhere near the lens. Okay, we're not interested in those rays either. Okay, because those rays, they just go off in whatever direction they want, and if they don't hit the lens, then they're not going to be bent by the lens. We're simply not interested in them. Then there are the rays which do impinge on the lens, and they're going to get deflected by the lens by refraction, and those rays are actually going to converge, and they're going to converge on the image. They're actually going to converge on the tip of the image. Because they're being emitted from the tip of the object, they will converge on the tip of the image there like that. If we had picked another point on this arrow, say halfway down, then those rays would converge on halfway through the image there like that, okay? But we're just going to pick one point, and there's the point at the tip of the object. They will converge on the tip of the image like that. All right, now there's an infinity of those, and we could trace all of those through, but that's kind of hard to do, okay? To see where the image is formed and what kind of image is formed and so on, you really only have to trace 3 out of those infinity of rays that are being emitted there, okay? And so what are those? Okay, what are those rays? I've got them drawn here, okay? And I've got them labeled as number 1, 2, and 3, all right? So how do these rays work? Let's take a look at how you would trace ray number 1, all right? So you could imagine just drawing this diagram out here, okay? So here's the focal point there, okay? I labeled them F2 and F1 just so that I could talk about them, these 2 focal points, but they're both the same focal length, okay? So don't think that just because one is F1 and F2 that they're different lengths, okay? So they're 2 different points, but they're both the same distance from the lens, okay? So let's take a look at how you would trace ray number 1. So ray number 1, if you go back here like this, ray number 1 is emitted from the tip of the object, and it travels parallel to the axis, okay? So it comes in parallel to the axis. It impinges on the lens, and you remember with the mirrors I just showed you, when something comes in parallel to the axis, what does it do? It gets bent such that it travels through the focal point. So the ray that comes in parallel to the axis impinges on the lens, it gets bent, and it passes through focal point F1 like that, okay? So you can see this ray right here starts from the tip of the arrow, travels parallel to the axis, impinges on the lens, gets bent by the lens such that it passes through F1 and then goes out, okay? Now I've got all 3 rays drawn there, but if you just drew this one ray, just ray number 1, you wouldn't know where the image is, Okay, you would not yet know where the image is because you would just see a ray coming in like that and then a ray going out like that, and you go, well, where is this image? Okay, so you need at least one of the other two rays. All right, so let's do ray number 2. Okay, what's the rule for ray number 2? So one of the things about these rays is it doesn't matter whether the ray, whether you trace the ray one way or you turn the ray around on itself. Okay, so even though there's an arrow which shows the direction of the propagation of the wave, if you were to reverse the wave's direction, it would still trace out the same ray, okay, just in the opposite direction. So a ray, number 1, a ray which comes in parallel to the axis goes out through a focal point. Conversely, a ray which comes in through a focal point will go out parallel. Okay, and that is ray number 2, which I've got labeled right here. Okay, so imagine that you start at the tip here of the object and you're a ray and you pass through focal point number 2, you come and you impinge on the lens, you will now go out parallel to the axis. Okay, so ray number 2 passes through the focal point and it goes out parallel. Now if you drew ray number 1 and you draw ray number 2, they're going to cross. And where do they cross? They're going to cross right there. They cross at the tip of the image. And that's how you find out where the image is formed. Okay, so ray number 1, just to repeat, ray number 1, ray comes in parallel, goes out through focal point F1. Ray number 2 passes through focal point F2 and then goes out parallel. Where the two cross, you're going to get the tip of the image. Okay, so, and that would be sufficient, but I've actually given you a third ray, ray number 3. Okay, so ray number 3 is another ray which you would have to do the geometry properly to see how it works, but a ray which starts at the tip of the object and passes through the very middle of the lens. That's the lens where the axis goes, isn't bent at all. Okay, and you say, well, why is that? And again, you'd really have to look at the geometry of this property and use Snell's law to work it out. But it turns out that a ray which passes through the very middle of the lens, the point at which the axis impinges on the lens like that, you can see it right there, doesn't get bent at all. Okay, so that ray would pass through the middle and then would pass out. And if you did this properly, it would also pass through the tip. Okay, so you've got these 3 rays, 1, 2, and 3, and they're all doing their own thing, but they all converge at that tip there, okay, the tip of the image, and that's where the image is formed. Okay, notice that the image is not formed at the focal point. A lot of people say, well, all the rays pass through the focal point, so the convergence must happen at the focal point. No. They'll converge somewhere, and it's not necessarily at the focal point. The only way they'll converge at the focal point is if all the rays are coming from infinity. Okay, and that's not the case if you have an object which is close to the lens. You can see that this object, you can see those 3 rays there. When they leave the tip, they're not coming out parallel. Okay, so they're going to converge somewhere else. Okay, so this is one of the points about the thin lens. Not only do all rays from infinity pass through one focal point, but rays from any object which is somewhere near the lens, they'll also converge, not at the focal point, but somewhere else. But they'll also all converge at one point like that. Okay. So there you go. Those are the 3 rays. And if you were to trace out those 3 rays properly, you would then get where your image is formed. Okay. And so there you go. Now, I'm not going to do the geometry of this, but if you did the geometry of this, okay, so that's how you trace these things out. But if you were to do the geometry of this, okay, let me just skip ahead here. What I'm skipping ahead in the notes is what I already described about how to trace those rays. Okay, I actually describe how to trace rays 1, 2, and 3. But once they're traced, what you could do is you could look at that diagram and go, oh, look, there's a whole bunch of similar triangles here. Okay, so similar triangles are triangles where the ratio of the sides are the same. Okay, one might be bigger than the other, but the ratio of the sides are the same. Okay, and I mean, I won't go back to the diagram, but if you take a look at that diagram, you'll see that there's a whole bunch of triangles there. And if you form all the similar triangles, you come up with a nice little formula. And here's the formula right here. This is number 1. Okay, sometimes called the lens maker's formula. Okay, it basically relates the focal length f to the distance of the object from the mirror and the distance of the image to the mirror. Not the mirror, sorry, the lens. Okay. By the way, it works also with mirrors. Okay, but we're going to concentrate on lenses. All right, which is why I said mirrors a second ago. But basically, 1 over the focal length is equal to 1 over the distance of the object to the lens plus 1 over the distance of the image to the lens. Okay, so there you go. All right. There's also another quantity that we can define, and it has to do with the ratio of the sizes. You might say, is the image bigger than the object? Is the image going to be smaller than the object? How does that work out? And the answer is that the ratio of the height of the image to the height of the object is the same as the ratio of the distances of the image and the object to the lens. Okay, and that's this formula number 2. M is called the magnification. Okay, and so M is going to equal negative DI divided by DO, and that's going to equal HI over HO. All right, at this point I've got to tell you something about this sign. All right, so let's go back to the diagram up here. Okay, and actually let's go back to this diagram here. Okay, the way I've shown you DO and DI here, DO is positive and DI is positive. Okay, but HO is positive and HI in this diagram is negative because the image is inverted. Okay, so when you have an inverted image, the ratio of HI to HO is negative. Okay, because HO is positive up, HI is negative down, and so a negative divided by a positive is negative. Okay, but the way I've got the DO and DI defined here, DO is positive and DI is also positive. Okay, and so this formula here, the way it needs to be interpreted, the magnification formula, is if DO and DI are on opposite sides, the way you saw a minute ago, they're both positive. When you form the ratios, of course, DI over DO is positive, but the negative sign in front makes it negative, and you need that because HI is actually negative in this formula. Okay, so the magnification, to summarize, the magnification, it's given by this. If the magnification is negative, what that negative means is that the image is upside down or inverted with respect to the object. You'll see as I go through and I trace some of the other lenses, okay, that you can have HO and HI both up, okay, in which case the magnification would be positive. All right, so a negative magnification means that the image is inverted, but there's also just the magnitude of the magnification. If the magnification is bigger than 1, so magnitude, like just take the absolute value, never mind whether it's positive or negative. Okay, so if the magnification is bigger than 1, that means that HI is going to be bigger than HO in magnitude, not sign. Okay, so if M in magnitude is bigger than 1, that means HI is bigger than HO. That means the image is bigger than the object, and then you have magnification. Conversely, if M, the magnification, is less than 1, that means that the image is smaller than the object, and you have demagnification. Okay, so that's how magnification works. And so at this point, really what we need to do is start solving some problems. All right, and what you have here is basically just a restatement of what I just said in my notes of, like, when DI and DO and DI are both positive, then you're going to have HO is positive. HO is positive by definition. The height of the object is positive by definition. The height of the image, well, that depends. If it's inverted, it's negative. If it's not inverted, it's positive. Okay, and finally, before we jump in and start doing some problems, F for a convex lens is always positive. Okay, we'll see that when we get to the concave lens, F is negative. All right, so a few more terms. The orientation, I already said this, but it's worth saying. The orientation is when the image is upside down, it's called inverted. When the image is in the same direction as the object, when both object and image are in the same direction, the image is called upright. But when the image is upside down compared to the object, then it's called inverted. Okay, and this next point is a little hard to see right now, but you'll see what is meant by the image type when I do some of the other lenses later, some of the other images later. But this image is called a real image. Okay, and why it's real is because it is formed by the convergence of rays. Okay, so whenever an image is formed by rays converging onto the image, you actually have to put a screen here, and the image is projected onto the screen, and that's called a real image. Images that are formed by diverging rays, which we'll see later, and so it's a little hard to get your head around why you need to make this distinction between real and the other type of image. Those other images for diverging rays are called virtual images. Okay, by the way, this is the way the human eye works. Okay, so the human eye, there's some object out there, all right, and the object out there emits rays. The lens of our eye then focuses onto the retina. Okay, so where the image is on the retina, the rays have to converge onto that image. And the human eye, the way it works is it'll change the focal length. Okay, and you can't do that with fixed lenses, but the human eye will stretch and contract your eye lens. This way you can focus the image onto the retina. Okay, and so for real images, the rays converge, and to see the image you have to have them converge onto a screen. Okay, so those are called real images. The virtual images, which you'll see in a minute, those are formed because of diverging rays. All right, okay. Oh, I guess before we do a problem, let's I actually have here that we're going to go through the other situation with a convex lens. Okay, so with a convex lens, just to get the point of the virtual images, here's another possibility. You can have where the object is closer to the lens than when the object is closer to the lens than the focal point, you're not going to get the same kind of image. You're not going to get a real image. So what I've got here is I've got an object, and this object is actually closer to the lens than the focal point. So here's the focal point on the one side, and here's the focal point on the other side. You'll see that in the previous diagram here, you'll notice the focal point was here, and the object was actually further from the lens than the focal point. If, however, with a convex lens, we put a object closer to the lens than the focal point, you're going to get the virtual image. Okay, so let's take a look at that. Here's the focal point here. Here's the focal point also on the other side. Okay, it's a little harder to see, but there's a focal point there and a focal point here. Notice that the object is closer to the lens than the focal point. Now, if we trace out rays 1 and 3, ray number 1, remember what it does is it goes out parallel. Okay, travels into the lens parallel, and then it gets bent by the lens and passes through the focal point. So there you see it coming in parallel and then passing through the focal point like that. And then I chose ray number 3 because that's the easiest one to do here. Ray number 3, remember, passes through the middle of the lens and goes out straight. And notice that now rays 1 and 3, they don't converge together. They're not coming towards one another. They'll actually never pass one another. They diverge. Okay, this is when you get the virtual image. And so now you say, well, how am I going to see this image? Because if you put a screen here, no matter how far from the lens you put the screen, you're not going to get an image at all. The way the image is formed is you have to look back through the lens with your eye. So I've drawn here your eye. And if you take a look, it looks like ray number 1 is coming from this dashed line back here. And it looks like ray number 3 is coming from this dashed line back here, like that. And ray 1 and ray 3, they both appear to be coming from this point back here, and that's where the image is formed. Okay, so you can see here that this image is not formed by rays converging on the other side of the lens, because the rays are diverging on the other side of the lens, but they look like they're diverging from an image on the same side of the lens as the object. Okay, so if I trace just follow back ray number 3, it looks like it's coming from this dashed line here, and ray number 1 looks like it's coming from its dashed line here. Those rays look like they're coming from that point there, and that point is the tip of the image. Okay, so here's the object. It's emitting ray number 1, and it's emitting ray number 3. Ray number 1 and ray number 3 appear to be coming from an image behind the lens on the same side of the lens as the object, and there it is right there. There's the tip of that image. Okay, and so this is known as a virtual image. Right? It's a virtual image, and the reason is that it's not formed by rays that are converging onto the lens. Rather, it's formed by rays that look like they're diverging from the image, and you can only see that by your eye. Okay, by the way, this is how a magnifying glass works. So a magnifying glass, you have to put the object closer to the lens than the focal point, and then you look through the lens and you will see an object which is bigger. And you can see here the object is small compared to the image. Okay, and the other thing you'll notice is that the image is upright compared to the object. So it's not inverted the way it was before. It's also upright, and it's bigger. Okay, so there you go. There's the story with a magnifying glass. Okay, by the way, in this case, the distance from the object to the mirror, that's positive. That's always positive. The height of the object is always positive by definition, and the distance of the object to the mirror, to the lens, is always positive. But because the image is on the same side as the object. In this case, so in this case over here, when you're measuring the distance of the image, that's from there to there, because it's on the same side as DO, DI is now considered negative. Okay, so for our convention, when both the object and the image are on the same side, DO is positive, but DI is negative. Okay, but the height of the object is positive by definition. The height of the image is also positive. Okay, so this image is upright because it's in the same direction as the object, and it's virtual because it's not formed by the rays converging, it's actually formed by the rays diverging. Okay, so there you go. All right, I guess I'm going to do the last example of the convex lens before we actually jump into problems. Okay, so the last example that we're going to look at, so we looked at two situations with the convex lens. One was the object is further from the lens than the focal point. The other one was the object is closer to the lens than the focal point. Okay, and those are the two possibilities for a convex lens. And finally, let's look at a concave lens, the rays for a concave lens, and then we will solve some problems. Okay, so for the concave lens, what we have is here's our ray diagram. So you'll notice here, this is the lens, and the way the lens is drawn is kind of like you would draw the concave lens, but the arrows are actually pointing the other way to show that the lens is actually flaring at the edges. So for a concave lens, the endpoints, the tips of the lens, have to be thicker than the middle. So the middle has to be thin and the edges have to be thick. Okay, and that's what this diagram or the schematics here is trying to indicate, like that. Okay, the rays work a little bit different though. The rays now, so here's the object. Okay, and here's a focal point f1 and f2, and both f1 and f2 are the same distance from the lens. Okay, and the object is right here, and now we have we could trace out three rays, but I'm just going to trace out two of them because that's all you really need. Ray number one, okay, comes in parallel to the lens, to the axis of the lens. So here's ray number one coming in parallel to the axis of the lens, and now for the convex lens, it would bend and pass through f2. For the concave lens, it bends away from f1. So that's a little bit confusing, but what you could see here is here's the ray, it comes up to here, it gets to the lens, and now notice that ray number one is kind of flaring out, it kind of bent out like that, away from the axis. You say, well, how do I determine what direction it's going in? It bends such that it's like traveling directly away from f1. So you see that dashed line there, f1? There you go. That's where ray number one appears like it's coming from f1. So it comes in parallel, but then it bends such that it appears to be traveling away from focal point f1. Okay, on the same side of the lens as the object, and that's what that dashed line is. All right. Ray number three is the easiest one in this case. Ray number three passes through the middle of the lens and just goes out straight. Okay, so here's ray number one again, comes in parallel to the axis and then bends away such that it's traveling away from f1, and then ray number three passes through the middle of the lens and just goes straight. Okay, now you might say, all right, well, these two rays, ray 1 and 3, they're diverging, so this lens diverges. By the way, in this case, it doesn't matter whether the object is closer than the focal point or further from the focal point. For the concave lens, the image is always virtual. The rays always diverge on the other side of the lens. Okay, so they're always going to diverge on this point. That means to find that image, you have to trace back ray number one, and you have to trace back ray number three, and you say, where does ray 1 and ray 3 appear to be diverging from? And here's where they meet. Okay, I know one goes all the way back to f1 there, but all you have to do is look where ray number one appears to be diverging from and ray number three appears to be diverging from right there. And that's the tip of the image. Okay, so there's the tip of the image and there's the image right there. Okay, notice that for this lens, the image is upright. Okay, so it's the same direction. It's on the same side of the lens as the object and it's smaller. So this is what's also could be called a concave lens, could also be called a demagnifying lens, okay, because it makes things smaller. All right, and there's only one case here in the sense that it doesn't matter whether the object is, you know, on the one side of the focal point f1 or on the other side of the focal point. Even if I put the image out here further than f1, it would still form a virtual image. It would still be a diverging lens. Okay, so you don't have to worry about two cases for this one. The convex has the two cases: is DO bigger than F or smaller than F? Okay, but in this case, it's always going to be diverging. All right, so I've summarized that here. In this case, the distance from the object to the, well, DO is always positive, just by definition, okay? But because the image is on the same side of the lens as the object, DI is considered negative here, okay? It's only when DO and DI are on opposite side of the lenses that they're both positive. If DI is on the same side as DO, then it's considered negative, okay? That's just the convention by which that formula was derived, okay? But an HO is positive, but the image is also in the same direction. They're both upright. So HO and HI are both positive here. And for the concave lens, the focal point has to be negative for the purpose of our formulas. Convex lenses, positive focal length. Concave lenses, negative focal length. Okay, now we can do some problems. All right, so here's a problem. A convex lens has a focal length of 10 centimeters. We place an object 15 centimeters from the lens. Okay, so what questions could I ask? Where is the image formed? All right, is the image inverted or upright? All right, is the image real or virtual? And what is the magnification? Okay, now before we jump in and actually do the numbers, we can already say whether the image is inverted or upright or real or virtual, and that's because you could just decide which case are you in. So we're in the situation where the object, so we've got a convex lens, that's the first thing. Okay, so there's two cases, and DO 15 centimeters is bigger than the focal length of 10, and so we're in the case where you're going to get a real image that's inverted. So the image is going to turn out to be inverted and real. Okay, and then let's work out what the how far DI is, or how big DI is, and what the magnification is. Okay, so here's the formula. 1 over F is equal to 1 over DO plus 1 over DI. Okay, the focal length is positive 10 centimeters, convex. So positive focal length. Okay, watch it, because I'm not going to say whether the focal length is positive or negative directly. I'm going to say, look, it's got a focal length and it's convex. Then you need to know that F is positive. Okay, and DO, the distance of the object to the lens, it's always positive by definition. So it's 15 centimeters. Great. We can now plug into this formula, and we're solving for DI, because I said how far is the image from the image? Yeah, how far is the image from the lens? So just DI here is equal to 1 over F minus DO. So that's equal to 1 over 10 minus 1 over 15. We'll work in centimeters here. Okay, and that turns out to be 30 centimeters. Okay, so the image is formed 30 centimeters on the other side of the lens than the object. The object is, 15 centimeters from the lens on the one side, and on the other side, the image is formed 30 centimeters from it. Okay, and the image, the eye is positive. Okay, so that's what tells you that it's on the opposite side. All right, the image must be real because it's formed by converging rays. All right, and that's just, you could sketch the ray diagram. And then finally, the magnification is given by that formula minus DI over DO. And that minus sign is important because now if you put DI as positive 30 and DO as positive 30, you're actually going to get -2 for your magnification. And you say, well, what does that -2 mean? Well, there's two things here. First, the negative means that the image is inverted. Okay, so, because HO is always positive, that means that HI must be negative. So the image is inverted. That's what that negative says. It also says that the magnification is 2, just in absolute values. That means that the image is twice as big as the object. The image is twice as big as the object, but inverted. Okay, so there you go. And that answers the our first question. All right, so here's another example. Repeat the previous problem, but this time assume that the lens is concave. All right, so the numbers are the same, but the focal point is got, when you put the value in for the for F in the formula, this time you have to put in -10 centimeters. Why? Because it's a concave lens. Okay, so we're solving for the distance of the image to the lens. Okay, so that's going to equal 1 over DI is going to equal right here, 1 over DI is going to equal 1 over F minus 1 over DO, just rearranging that formula. Substituting in for F, we're going to put in -10, so we get -1 over 10 minus 1 over 15, and that, working that out, gives us di is negative 6 centimeters. Okay, negative 6 centimeters. So negative 6, the fact that di is negative, tells you that the image is virtual because it's on the same side of the lens as the object. So when the object and the image are on the same side, you say, well, how do I see such an image? It's happening because the rays are diverging from the image, and so it's a virtual image. Okay, so I guess you can say two things about the negative sign there. The fact that di is negative tells you, one, that the image is on the same side as the object, but it also tells you that the image is virtual. Okay, so great. Next thing, and that has to be the case because the image is always virtual for concave lenses. So as soon as you hear concave lens, image is virtual, period. Okay. Now let's plug into the magnification formula, minus di over do. Notice that di is negative, so you got negative 6 over 15, which gives you 0.4, which is a positive number. So the fact that the magnification is positive tells you that the image and the object are both in the same direction. In other words, the image is upright. Okay, the image is upright, but that 0.4 tells you that the image is only 40% the size of the object. Okay, so this is your demagnifying lens. All right, so this situation here is precisely this this situation right here. Okay, where you have, you know, your object here. Okay, and this is your demagnifying lens, your concave lens. All right, so the rays, when they pass through that lens, they'll diverge, and the fact that they're diverging means that it has to be a virtual image. And here's the image. The image is erect or upright. Okay, so both the object and the image are in the same direction, upright. Okay, like that. And the image is smaller than the object. Okay, so there you go, and that's what we found down here. Okay, so that's it for ray optics. And the only tricky thing about ray optics is the formula is a pretty simple formula. It's, well, there's only two formulas. It's this one right here, okay, and the magnification formula right there. Okay, so the only thing you have to be careful about are the signs. Okay, so if you go through these problems again and you look at the different possibilities, you know, just be careful with the signs, interpret the signs the way I did here, and you'll get it right. The only problem I didn't do is the situation where you have a convex lens where the object is closer than the focal point. Okay, but you'll probably see one of those in your assignment. Okay, thank you very much. That's the end of the lecture. Bye-bye.